Now that we know about several different types of thermodynamic process, that is an isobaric, constant pressure, isochoric, constant volume, isothermal, constant temperature, and now the adiabatic process, I want us to use those to put together some examples of cyclic processes. And the reason for looking at cyclic processes is this is sort of the fundamental way we think about generating usable energy for running our modern lives. And so what we're really interested in doing is taking heat and transforming it into work, into mechanical work. Okay, so that's really our goal at this point. And sometimes that mechanical work is just in the form of a generator, which can then turn and give us electricity, which at the other end will get mechanical work back out very often. Okay, so a cyclical process is one where we start at some point and we end back at that point. So the important thing to note is that if we start at some point here, at some pressure and volume, right, this is the volume and the pressure, then that's at a given temperature. By the time we get back for a cyclical process, the change in temperature over the whole process is equal to 0, so the change in internal energy is equal to 0. And so that means by the first law that the heat is equal to the work total, right? The heat that's in and out. So this is the heat in plus the heat out must equal to all of the positive and negative work that's done, okay? So work positive plus work negative. And so if we look at a process that we looked at before, which is this isobaric, this square, because the work is easy to calculate. It's not so easy to make this kind of a process, but this isn't so hard to set up, and it's certainly not too hard to imagine. So this is along this first section here, this path A, if you will, B, C, and D, we can calculate the work done, and we can see that the work in, first of all, the work for B is equal to the work for D is equal to 0. So there's no work done on these sides because the volume isn't changing. Our work, of course, just to remind ourselves, is the integral P dV, and of course if dV is 0, then this whole thing goes away. On A and C, the pressure is constant, it can come out. So for work A and C, this is pressure times the change in volume. Notice that for work A, this is greater than 0 because we're going to a bigger volume. Work C is a lower pressure. This is less than 0, so that's this area under the curve here. And so what we're left is the difference between A and C is this area in here, okay? So that's the work that's done. So when we add these up, pressure A, pressure C, we have the same delta V, then the work total is just going to be pressure A minus pressure C, that difference times this delta V. Okay, so that's our work that's done. Now, we can look at what heat goes into giving us this total amount of work. And we can look at it in terms of, right, we had our equations for heat transfer with constant volume and heat for constant pressure. So Q for constant volume, sorry, that's a Q volume, is equal to 3/2 for monatomic nR delta T, and for constant pressure, I'll put this over here on the constant pressure side, QP is equal to 5/2 nR delta T. Okay, so we can look and see what happens in all of these situations. It's worth noting, though, where we're at higher and lower temperatures. So I'm going to just sort of sketch in some isotherms here. That is some constant temperature curves. So when we look at our pressure versus volume curve, this that would be one temperature curve. Then we could have another one kind of going like this. Ooh, that's not really great, but anyway, like that. And this is a higher temperature than this. So this would be T1, T2, and we can keep going. Ooh. Like that. There's T3, that's at a lower temperature, and then finally we'll pick up this last temperature. The only reason for putting these isotherms in so this is an isotherm, constant temperature, is so you can really easily see if we're going to a higher and lower temperature. So as we go here, step A, notice we're going to a higher temperature. So step A, we have constant pressure, so Q for A is greater than 0 because our final temperature here is greater than our this temperature is greater than where we started. So this step A is where we have heat going in. Step B, we're going from a higher to a lower temperature, right? Because we're going from 1 to 2. So step B is less than 0. So this is a Q out. This diagram is going to have lots of parts now. So this is our heat in step. This is a Q in step. This is heat leaving, heat out. Okay, step C is going the other way. We're going from a higher to a lower temperature. So this is also a heat out. And this one is the opposite of B. So this is a heat in. Okay, so the point here is that I have some heat going in and also some heat going out. And typically when we set up these systems, the heat coming in is coming from our energy source, our fire. We hope we're not burning a lot of things, but we still are burning fossil fuels. We are in some places burning wood to do this, but if we're going to generate work, we put heat in. But there are also some steps if we're going to get back to the same place. So this presumes it's cyclic, that it does get back to the same place. There's also some places we have to expel heat, and this is in the form of exhaust. So the Q out is in the form of some exhaust. And we'll see where this comes in a little bit later, but so you can get a sense of that. And when we talk about the efficiency here, what we're interested in is how good a system is at taking our heat in and turning it into work. So we measure our efficiency as the work total, the work we get out, so the positive take and without, the negative. So this pink area over whatever we had to spend to create this system. Because Q in is what we pay for. We pay for this heat going in. That's what we buy our gasoline for. This Q out is generally not usable for us. It's exhausted into the environment as thermal pollution. There's a good example of that across the bay. Some of you may have gone in when it's cold. You know that manatees sort of gather near the power plant over in Apollo Beach because that's where the exhaust is, and it's a little warmer there. That's a section where exhaust heat is coming actually into the bay, and it's warmer, and so manatees are happy to be there. And so that's maybe good for the manatees, but it's also, there are places where this exhaust heat causes some real problems to aquatic wildlife because the temperatures are higher than they're supposed to be typically. So we're going to focus on this efficiency because if we want to address our energy use, our energy consumption, one way we want to address this, besides just reducing what we do and the sources of energy that we use, that is the burning of fossil fuels, we really would like to increase our efficiency. So we'd like to get more work out for the heat that we put in. Now we certainly can't get, just from energy conservation, we can't get more work out than we put in. That violates energy conservation. But it turns out it's worse than that. We always have some output heat, some exhaust that turns out to not be very usable. So our picture generally for these types of cyclic processes, these repeating processes, which is really what an engine is that we, from energy conservation, we have heat in because we end up, this is at the same place every time. Our internal energy is 0, so the heat in goes into work, or it goes into our heat out, right? Our Q out. And so these two have to equal our heat in. And the trick is that what we want to do is increase this work that goes out and decrease. So we want this to be a bigger arrow, and we want our work out to be a much smaller piece. That's an increase in our efficiency. So efficiency of engines, oh, that's off the screen, sorry. So the efficiency of an engine is given by, the work that we get out over the heat that we get in. And we want this to be as close to the full width of this as we can, okay? That's the idea. That's the goal in creating more and more efficient systems. It turns out that the most efficient system that we can make, for reasons that we'll get to eventually, but for right now, we're just going to see how we calculate the efficiency of it, is with a Carnot engine. So a Carnot engine is one that is a combination of isothermal and adiabatic processes. 2 of each to make a 4-step process. Engines don't have to be 4 steps. They can be multiple steps. You could be 3, but this is a typical setup. So here is the PV diagram, and we'll go through it sort of step by step here. This is going to be my T high, and this is going to be my T low. So I've got 2 temperature reservoirs that I have nearby. The hot one is maybe boiling water. The low one is cold water. That's not a very efficient engine, as we'll see later, but it's very hot somehow. It's heated up. You burned something to get it nice and warm. And so the first step will be, if we take something and if we take our container and we put it next to this, we put it in next to this high temperature reservoir, okay? So we have our gas with a piston that can go up. This is sort of the typical situation. So you can think of this piston as being attached to a gear or a wheel that's turning around. So as this goes up and down, it then makes something turn, okay? So as we put it near high temperature, we keep the pressure the same. We put our gas container next to this high temperature reservoir. And so the temperature stays constant. So let's think of PV equals nRT. The temperature stays constant. So this expands, right? So this goes up. We've got positive work. It expands. And as it does so, right, the pressure is going to have to decrease if we're going to stay on this isotherm. So that's step A. So this increases up. Then what we're going to do is even have more expansion, more work. So this is the work for A. So our next step will be a situation where we replace this now with an insulator. We still have our same tank here. This is our tank that has gas with the piston. And so now the piston can go up higher. Again, you can just think of this as a lever arm that can go up as we're at a situation where it's insulated and this expands further. Expands on the adiabat, so it goes sort of like this. This is steeper, like that. Okay, so this is my adiabatic process. And so in this case, the Q is equal to 0, and we have a temperature change, a volume change, and a pressure change. And that's all given by this pressure times volume to the gamma is equal to a constant, or we have TV gamma minus 1 is equal to a constant. Okay, and then we take this and we put it back next to our, so this is step, let's call this A, this is B here, and C, now we're going to put it at our low temperature. Oh, suddenly became very small. Okay, here's our piston. This is our T low. So this is an isothermal situation. And so in this case, it's at a lower temperature, which is what it got to after the expansion, right? It expanded. And so it got to a lower temperature. And now along this temperature, we'll compress it a little bit. So the volume gets smaller. So volume gets smaller means we go that way. So we're going to go this way a little bit. That's step C. And then eventually we will then return with an adiabatic process. This is really steep. So this is D. So D takes us back to our insulated situation. Ooh, there. We're insulated again, and we're compressed even further, okay? So we have work that's in this direction. Something's pushing it down, if you like. Okay, so the area that we have, the work that's done, is the area in here, okay? And so what we're going to do is calculate the total work that's done, and we're going to look at the heat in and the heat out. Now, the heat in and heat out are actually pretty easy because there is no heat on B and D. This is adiabatic. The heat is equal to 0. So we have heat associated with A. We have heat in on A, and we have heat out on C. And that's all we really need to worry about for the heat, okay? So heat in on A and out on C. And then, and we'll look at how we calculate those in a minute. And then when we look at the work, notice that for the work for B, it's an adiabatic process. Q is equal to 0. So that means the work is equal to minus the change in internal energy for B. Well, the change in internal energy for B is related to this temperature difference, right? It's 3/2. For monatomic, it's 3/2, whatever the gas is. We put a different number up here. N, we haven't changed the number of moles. R is a constant. Delta T. So the work for B and the work for D, also minus change of internal energy, they have, one is positive and one is negative. So this is positive work. This is positive work, negative change in internal energy, and this is negative work, positive change in internal energy. But these added together just give me 0 because they have the same delta T, and our Q is 0, so internal energy is proportional to the work. So when I want to find the total work, I don't even need to worry about finding the work on D and B. Same thing for the heat, okay? So really we're going to pay attention to steps A and C, all right? So steps A and C are isothermal steps. All right, so we're going to focus on the work done on steps A and C. So A and C are isothermal. So the work done for an isothermal process is equal to nRT, or T is constant, right, times the natural log of V final over V initial. And we just got that by taking the integral of P dV, and that gave us the natural log. Go back a couple of videos if you don't remember seeing this. Okay, so for step A, we have the work for A, that would be the area under this curve right here, okay, that's positive, is going to be in R, this temperature is temperature high, natural log of, now I've got to label some V's, some points. So this is going to be 0.1, 0.2, this is going to be 0.3, and 0.4. So natural log then of V2 over V1. That's the work for A. The internal energy is 0. The change in internal energy is 0 because it's the same temperature. So the heat that's going in is the same thing as this. So the Qn is equal to Nr, temperature high, natural log of V2 over V1. Okay, so that's nice. For part C, we have the work for C is just going to be Nr, temperature low, because we're on the low temperature part. We're on this part of the isotherm. And that's going to be natural log, the final is V4 over V3. And in this case, 4 is smaller than 3, so this is going to, in fact, give us a negative number. Okay, so if I'm going to find the efficiency, what I'm going to do is take this minus this plus this one is negative, and divide it by our Qn, okay? So our efficiency over here, efficiency is our total work over our heat that came in. So our efficiency is, putting all of this in, I'm going to say nRT high, natural log of V2 over V1, plus nRT low, natural log of V4 divided by V3. All of that is going to be over this Qn, this nRT high, natural log of V2 over V1. Every term has an N and an R, so these can go out. And I can actually, when I've got something like this, I've got something on the denominator, I have two terms, right? If I have 1 plus 3 divided by 4, that's the same as 1/4 plus 3/4. So this is, the efficiency is equal to then temperature high, natural log of V2 over V1 over temperature high, natural log of V2 over V1, plus then temperature low over temperature high, natural log of V4 over V3 divided by natural log of V2 over V1. This is kind of a mess. This one is nice. This top and bottom cancel, so that gives me a 1 here. And then I got to deal with this term. And so I need to use something about an adiabatic process to deal with this term. The first thing I want to do is I want to make everything a positive number here. And V2 is bigger than V1, so that's positive. But this one I can just make into a positive by saying, by using a natural log rule, which is, here I'll just write this, E minus T low over T high, natural log, if I flip these, now it's 3 over 4 over natural log of 2 over 1. If you remember your natural log rules, right, natural log of x to the minus 1 is minus natural log of x. So you can invert whatever's inside the natural log by changing the sign out here. Okay, so this way I just know those are two positive numbers. Okay, now what we need to do, because I want to relate 3 and 4 and 2 and 1 to each other. And 2 and 3 are on the same adiabat, right? They're on this curve. And 1 and 4 are on the same adiabat, which means there's a relationship between those. Okay, so for the adiabatic process from 2 to 3, the thing that's true about 2 to 3 is that pressure of 2 times volume of 2 to the gamma is equal to a constant, right? And pressure of, and that's true, and that constant is also pressure 3 times volume 3. So you get something that looks like this, is equal to P3 volume 3 gamma. Okay, The other relationship that also holds, besides this one, is that temperature to V2 to the 1 minus gamma is also a constant. So that means I've got this as T3 V3 1 minus gamma. Now, T2 is temperature high. So I'm going to write that as high. T3 is temperature low. Okay, so that's my 2 to 3 relationship. I've got a similar thing going on if I look at from 4 to 1 or 1 to 4, right? That tells me it's also an adiabatic process. I've got P4 V4 to the gamma is equal to a different constant, 2, a different constant. It's not the same constant as up here, but what is true is that P4 V4 to the gamma equals P1 V1 to the gamma. And so I can have this, I'm going to just skip to the second type of relationship, which is temperature 4 V4 to the 1 minus gamma is equal to temperature 1 V1 to the 1 minus gamma. These are not equal to each other. This equation is equal to some constant. That's equal to a constant, and this is equal to constant number 2, for example. Now, T4, let's just make sure we know, that is the temperature at point 4, which would be temperature low. T1 is the temperature here, which would be temperature high. Okay, now I've got something that's going to relate some things to each other. It's not easy to see, but let me sort of highlight what we've got. I've got this equation, and I've got this equation. And what I'm going to do is, notice I've got one that's got a T high and a T high and a T low and a T low. So I'm going to divide, I'm going to take this equation, I'm going to divide it by, actually I'm going to take this equation and divide it by this one, I think, so I can get the relationship. So I'm going to take this first equation, T high, V2, 1 minus gamma is equal to T low, V3, 1 minus gamma. And I'm going to rewrite my second equation here. So this is my second equation right here. I'm going to put this over, I'm going to just switch sides. So this is going to be T high, V1, 1 minus gamma is equal to T low, V4, 1 minus gamma. Now, you can divide, as long as you divide an equation, both sides by the same thing. Like you can divide both sides of an equation by 2 or both sides of an equation by 1,000,000, it doesn't matter. What I'm going to do is I'm going to divide this top equation by the bottom equation. So I'm going to divide this side by this, but since this is equal, I can divide it like that. And the reason for doing this, I hope you'll see, is that, hey, the temperatures go away, and I'm left with, look at this, I'm left with V2 over V1 all raised to the 1 minus gamma is equal to V3 over V4 all raised to the 1 minus gamma. You can take it to sort of the square root of whatever 1 minus gamma is. If 1 minus gamma is half, then you can square the whole thing, for example, to get rid of this 1 minus gamma. Or you can say you can raise this all to the power of 1 over 1 minus gamma, whatever you want to do. In other words, for this term to equal this term, what's inside the parentheses has to be equal to each other. And what that says is V2 over V1 must be equal to V3 over V4, which is really convenient. I had to know where I was going to make sure I didn't spend too long getting there. It means that this term right here is equal to this term. So they cancel out. And after all of that, my efficiency is just 1 minus T low over T high. Now we can start to see why we can't get an efficiency of 1. To get an efficiency of 1, I need my low temperature to be 0 Kelvin. But this would say to get an efficiency of 1, I need absolute 0, or I need a high temperature that's an infinitely high. Now we can get really high temperatures, but we can't get to infinity, which means that we can get efficiencies close to 1. What we're looking for is the high temperature side of this equation. We want the high temperature to be really high, not close together. We want a curve that's way up here so I can have a much bigger area. And we want the low temperature side to be as low as possible. So when power plants and stuff are looking to exhaust, they tend to look for cold exhaust places. It turns out, you know, basically cold streams, bodies of water tend to be nice places to exhaust to. And then this high temperature, this is where we make most of our work, is try to, how can we get a really high temperature so we can have a higher efficiency? Okay, now this is for this particular cycle. And it turns out that there's a proof that says that this is the best you can do. If you've got an engine that's working between two different temperatures, which you have to have two different temperatures if you're going to get back to the same place, that if you have an engine working between two different temperature reservoirs, this is the best you can do. It's called the Carnot efficiency. Carnot efficiency. And you can't do any better. And generally, not a surprise, you do worse. So the efficiency that we calculate for an engine is given by this. The ideal efficiency, the best efficiency we can have when we have two temperature reservoirs, is given by this. Okay, so this is the best. So in general, we're going to have efficiencies calculated this way that are going to be less than whatever we get here. Okay, and if we're looking at room temperature, then we're looking at temperature low of about 300. So we'd like this to be like in the thousands, so we can get a decent efficiency.